midnight. Just a reminder. Any questions about homework? Is it smoothly? Okay. So a couple of other quick announcements about the schedule. There is just a meeting posted for next lecture on Thursday. So after you're done with homework, take a look at that. It's a paper by E.T. James, who's kind of one of the really important people in the history of Bayesian analysis. And it's not a very technical paper. It's kind of long. It's about 20-some pages. So give it a read, and try to get through it by Thursday. But you don't have to understand every single detail. But it's going to be the topics that we're going to talk about Thursday are going to be in that paper, or a lot of them are going to be in that paper. The other point is today's lecture. We're going to be talking about exponential families and conjugate priors, and I put a couple links to just the Wikipedia pages for exponential families and conjugate priors because they're very detailed. It's more information than we'll even cover in this lecture, in this class. It's basically everything you ever wanted to know about these topics. There's a good Wikipedia page for it. That's not always going to be the case for every lecture that the Wikipedia page is comprehensive, but this is one case where I don't think I can write notes that would improve upon the Wikipedia page. So everything we're going to be talking about you can kind of find there, and if you follow links throughout the Wikipedia pages. Okay, so that's kind of just where we are. Oh, and then the next homework I'll probably post. Not today, since everybody's presumably still busy with homework 0. I'm going to probably post it tomorrow or Thursday. So the next homework will be coming right on the heels of this homework, but I'll wait a day or two to post it. And you'll have another couple of weeks for the next one as well. Okay, so that's where we are schedule-wise. Any questions? All right. Okay, so let's talk about first conjugate priors. So as we've talked about, Bayesian models, you need a likelihood model, probability model, and then you need there's parameters to that likelihood, and those parameters under the Bayesian paradigm have to also be random variables, and in that case, they need to also have their own probability distribution, which is prior, right? And so we've looked at one particular case, which is just very simple, just a reminder by the Bernoulli, which is the binary 0 or 1 random variable, and it has a parameter, we call it theta, which is the probability of being 1 versus 1 minus theta, probability of being 0. And we gave it first a uniform prior, then we showed that was more generally, we could write that as a beta distribution prior, or 1 theta. And it turns out that what we've seen already in the Bernoulli example is already an example of what's called a conjugate prior. So I'll just kind of, in English, say what a conjugate prior means before we get into the details. But a conjugate prior means basically that you have a family of distributions which are your prior distributions. And then when you observe data and add the likelihood into the mix, the posterior in the end turns out to be from the same family of distributions. So, so if you remember the beta Bernoulli example, when we gave a Bernoulli distribution of beta prior, we ended up with a posterior, which was also a beta distribution. So, so let's write that down. So we had, let's see, theta In the previous lecture, we talked about theta was a beta distribution with parameters, let's say alpha beta, and then our likelihood, so this was the prior on theta, and again, theta is a 0 to 1 probability, is what this parameter means, and then the likelihood we had was our typical Bernoulli random variable. If I had a sequence of these, let's say n observations, these guys were going to be, let me write down, they're Bernoulli with parameter theta, but let me write down, yeah, let's just write it that way. So these were Bernoulli, each of these were Bernoulli with parameter theta, and then we showed that if we put these together, multiply these together, we ended up with the posterior, which is the distribution of theta given the observed data. We saw that that was, again, a beta distribution, right? With, let's see, the parameter being alpha plus the sum of the x's, and then, let's see, I'm probably forgetting, I think minus or plus 1, and then beta plus n minus the sum of the x's plus 1. Okay, I think I got that right. So what we saw was that because of the form of the PDFs here, when you multiply these two together, you get the joint distribution, and there's a normalizing constant to finish off basic rule, but when you multiply that together, you again get a beta distribution. And so this is, in general, this same type of behavior happens whenever we have something called a conjugate prior. So whatever family of distributions your prior comes from, if you use this conjugate prior for a particular family of likelihoods, and we'll see lots of examples here in a minute, the point is that this same family for the prior shows up as the posterior. That's the general concept of a conjugate prior. And why is this important? Well, it turns out that it's actually very difficult when you're trying to, just for a general likelihood, when you're trying to come up with some prior distribution such that the posterior distribution is analytically tractable, meaning that we know the function of the probability density function in the end. That's actually very difficult to do. And in general, when I take two distributions, if I come up with just some different distribution for the prior here, if it wasn't beta, and multiplied it by this likelihood, I would get a posterior that I might not be able to analytically compute the normalizing constant and get, you can almost always multiply these two, if you have the two functions for this and this, you can always multiply those together. The hard part is getting the normalizing constant. Okay, so having a known distribution or family of distributions for the posterior is, in general, not straightforward. But when we use conjugate priors, it turns out that it is straight. I mean, not necessarily straightforward, but it's a known analytical solution for the equation, for the PDF, and so forth, for the posterior. And so the number one motivation for why you use a conjugate prior, number one motivation is mathematical ease of use. So it just makes your life easier if you use a conjugate prior. So whether or not a conjugate prior is a good choice for the particular data that you're working with, the problem you have is a completely separate question. But if you don't have any other considerations at the beginning, this is a good set of priors to try out if you have no other reason to use a different prior, just because it naturally falls out with an easy-to-use posterior. Okay, so that's kind of, yes, question.
What is the significance of +1 in the posterior?
Well, if you remember the beta distribution, let me just double check my notes from last time, just make sure I didn't get that wrong, because I have a tendency to get off by one errors when I do things. Yeah, I did get it wrong, according to my notes. Yes. Sorry. Yeah, thanks for pointing that out. Just to be completely careful here, let me just make sure. So in our notes, yeah, we did a prior. This is right, but I got the +1 wrong. I was getting confused because if you remember the beta distribution has a -1. Let me just write down to be careful. So if I look at the PDF here, it equals 1 over the beta function for alpha beta times beta to the alpha -1 and 1 minus theta to the beta -1. I was thinking I needed a +1 to counteract that -1, but according to my notes, I don't. So we then added this into there. Yeah, that's right. Yeah, this is right. Because here, if you remember our PDF, I'm going to write this down because we're going to go over this in a slightly different form as another example of how these conjugate priors work. So this would be good to write down now. So this likelihood, remember, we can write down as just the product, because they're independent, the product of each xi, not p, but pmf, right, because it's discrete. So the integers 0 and 1, so we call it probably a mass function. And we could write these down in the form theta so the product of each of these, and I can write an individual one down as it's probability theta if this is a 1, and it's probability 1 minus theta if this is a 0. So I can write it down that way, right? This product is over all the data. Okay, and then the point is I can make this into a sum of xi's and this into a sum of 1 minus xi's, which gives me n minus the sum of xi's, and that's how I got this sum and this n minus thing. You should notice this is in the same form by normalizing constant as this guy up here. So take the product of these two together, and all the exponents just add all up, and that's how I get this. And the -1 does come around and carry all the way through, so I don't need a +1. I was had that wrong, so thanks for catching me on that. Okay, so yeah, so that's what we did last time. And this, I'm going to leave, I'm not going to erase this middle board here until we get to a little bit later, because I'm going to come back to this example in just a minute. Okay, but that's just this general behavior of your prior being the same type of distribution as your posterior is very, very useful, because we can do things with this posterior when we know its functional form and so forth. Okay. Any other questions before we that's kind of the setup, yeah.
What if we know it's like, suppose say posterior is a gamma distribution. Maybe it's not conjugate, right, but it still makes it easy to track down, right? Yeah,
so we'll actually see gamma distribution is one of these conjugate prior, it comes up. But yeah, so I mean, okay, yeah, if there was some other distribution you knew that you could use as a prior here that ended up with some other known distribution, that would be great. So these matching don't have to be, it's not necessary. That's right. So this is a good point to make, is that if you're right, if I could come up with a different distribution that gave me a known form here, that would be equally mathematically easy. But it turns out that that's actually very difficult to do. Like it's very hard to come up with a distribution here and a distribution here that, when multiplied together, you get a third family of distributions that is easy to work with. And it turns out that almost all the distributions that, you know, we learn in our statistics courses and so forth that you use in order to do things that have names to them, I should say. So gamma, exponential, geometric, blah, 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 whatever you want to, if you can name the distribution, it's almost always in this framework somehow. And I'll kind of, and when we get to exponential family, we'll see that all these distributions that you can write as exponential families have this property, and it's almost all the famous name distributions that you're familiar with. It's hard to think of a named distribution that doesn't fall under this category. So in fact, I can't think of off the top of my head anything where you take two known families of distributions, multiply them together in a conjugate, or sorry, in a prior likelihood pair, and get a third. I can't think of any examples. There probably are some that I just can't think of, or off the top of my head. That's a good question to maybe for people to as a brainstorming exercise, we can try until the next lecture to think of if you can come up with two distribution families, like Gaussian and exponential, for instance, multiply them together and get a third family of distributions. There's probably an easy example. I just hadn't thought of that. It was a good brain teaser. Okay. All right. So yeah. So let's see. How do we, how do we then, maybe let's see a different example of a conjugate prior. So, other than Bernoulli, which is probably the easiest distribution to work with, the next probably most useful one is going to be your normal distribution. And so if I start with a likelihood that's a Gaussian or normal distribution, in other words, each of my x's here, my data given a mean. Oh yeah, by the way, I'm going to say known, like we were doing last time, I'm going to just for now say there's a known variance, sigma squared. We'll cover the case where the sigma squared is unknown, I think on Tuesday next week. Wait, anyway, we'll do it eventually, yeah. Somewhere on the schedule, maybe next Thursday, I can't remember. Anyway, the point is, we'll get to this, but for now, let's just assume we have a mean parameter mu, which we don't know, it's the random variable, but we don't have, we don't have a sigma squared parameter because we're going to assume it's known for now. So it's just a constant like 1 or whatever. So we'll have the notation, our data, x1 to x7 as usual. Given mu, which is a random variable because it's a parameter, the Bayesian sense are going to be distributed, the xi's are going to be distributed given mu as a normal distribution of mean mu and variance sigma squared. Okay? Now it turns out that the conjugate prior for the Gaussian is just very simply also a Gaussian. So for the mean, I should say, of the Gaussian is also a Gaussian, but you have to come up with some choice for the mean variance of that Gaussian. And so I'll call it mu naught and tau naught squared. And these we'll say are constants, okay, that you, the data analyst, have to somehow decide on before putting these together, okay? Now it turns out that we're going to show in gory details in just a second here that this is conjugate, meaning, again, that the posterior for mu, and again, the posterior for mu is now mu is flipping this conditional, right? So it's mu given the observed data is distributed also as a Gaussian with some mean, which I'm going to call mu sub n. And again, the zero notation, the sub-zero notation, subscript 0 is supposed to just indicate parameters of a prior, and the subscript n indicates parameters of the posterior within observations. So this is a somewhat standard notation for conjugate priors and posteriors. And it'll have some variance sigma n squared. Okay? And so now the question is, I'm just stating this as fact, how do we see that this actually works out? So if I multiply two Gaussians together in the end, and then flip which one's the random variable and which ones are the constants. So I change from x as being big random variables to u's being random variables. And I see why that gives me a given Gaussian. Okay, so that's kind of the goal here. And that will show that, yes, indeed, Gaussian is a conjugate prior to the mean of Gaussian. Now notice this one's a little bit different from the beta Bernoulli case in that the likelihood the prior and the posterior are all Gaussian. In fact, this is the only conjugate distribution where it's self-conjugate. So the normal is conjugate to itself. Again, if we just stick to the mean parameter to get the variance between. Okay? Okay, so let's see, why is this the case? So to see this, we have to first remember a trick from algebra, which is completing the square. So hopefully everyone's seeing, you have a quadratic. How do I complete the square of a quadratic? So just to remind everybody, this notion of completing a square. You have a quadratic which looks like, in general, a quadratic and just some variable x, ax squared plus bx plus c. And you want to write it as a square, like x plus some constant, parentheses squared. And then there's going to be a extra constant to at the end of that, which would be like a plus some fudge factor to make this equal to that. So that's the completing the square trick, if everybody remembers that. So in general, this thing is equivalent to just writing a times x plus b over a, 2a squared. So this is my x plus constant squared that I want there. But then if I multiply this out, I don't get exactly c there. I get really this thing squared. So I have to subtract this off and add my c back in to make it equivalent. So I get b squared over 4a squared, but then there's another a in there, so I just get 4a. Okay? So that's just reminding everybody, if I rearrange the square to be in this form. And why is this important? Because we're going to want things that look like x minus mu squared inside a Gaussian. Okay? And when we combine all these Gaussians here, we're going to want to, again, cram it back into the form of a Gaussian, which looks like x minus mu type thing squared on the inside. Okay? So this trick that we're going to do with the Gaussian, this isn't the only time you're going to see it pop up in this class. So this is an important trick to kind of pay attention to and make sure you understand. Because we're going to see it again first of all, when we do put the variance back into a Gaussian, and then we'll see it again when we get to multivariate distributions, because when we're dealing with higher dimensional data, we very often still use Gaussians, and we'll see there's lots of times where you have to do this kind of completely square trick. Get conditional distributions, marginal distributions, and follow through the Bayes rule, all these things. With the multivariate Gaussians, it'll come up again just in a multivariate form. Okay, right now we'll just stick with univariate. Okay. Right, so now if I look at a Gaussian, just the likelihood here, I'll leave off the subscripts for all the x's for the time being and just look at a single x given mu in my likelihood being a normal distribution. The PDF there is proportional to, so very often I'm going to use proportional to, meaning I'm going to throw off the normalizing constant because it's not going to be important for this particular argument. But as we all know, this looks like this, right? And so the first thing I want to do is just rearrange this. I'm going to actually go the opposite direction and uncomplete the square here for this example that's going to help us with the conjugate prior argument. And so if I expand this quadratic, I'm going to see fairly simple stuff. Everybody hopefully will agree with this. I'm going to put x's on the right side here. And then some constant which actually is going to be less important already. Oh, wait. Okay, so that's expanding out the quadratic, right? And this is C, this coefficient's B, this coefficient's A. The C is going to be somewhat irrelevant because we can always take whatever constants we get in the end out here because they don't depend on the thing we have a distribution of. They can, if we have something else in there, we can always suck it into the normalizing constant, right? So this would factor out if it came out to something different, and we could always, because we're proportional to, we've got a constant here, we can suck that into. So in the end, this quadratic has an A value of -1/2 sigma squared, a B value of mu over sigma squared, and a C value of minus mu squared over 2 sigma squared. Okay, now the main point I want to make here is the following, and then why am I writing this down as ABC coefficients of a quadratic for a Gaussian inside the exponent. The following point is that if you have anything, if you know that your distribution for some random variable x is of the form proportional to e to the minus ax squared plus bx plus c, then you know this thing's a Gaussian, or else it's not a distribution. If a is positive, then you're in trouble, but a should be negative, or else this thing won't normalize to anything finite, so you can't make it a distribution. But assuming a is negative, anything of this form is a Gaussian. Okay? So you should convince yourself of that. It's fairly easy to see that. Essentially, again, I complete the square, so I get it into that form, and I know exactly what my mean and standard deviation are, and whatever c is, that c minus b squared over 4a, wherever that is, doesn't really matter. It gets, again, sucked into the normalizing constant. So no matter what I give you for coefficients a, b, c, again, as long as a is less than 0, so I can actually normalize this quadratic, you'll get a Gaussian distribution. No other distribution looks like that. Okay? So if we can multiply these two together and just show that it looks like e to the some quadratic formula in mu, then we'll know that as a distribution of mu, we've got, again, a Gaussian. So that's kind of what we're going to do. And also, what we can then do is, if we get the coefficients in this form of the quadratic, and now random variable will be mu instead of x, because we want to flip the conditional. If we get our quadratic in this form, then we can just read off, if we know a, then we'll know, just by rearranging this formula, what the standard deviation is, or I should say the variance parameter is, the sigma squared. In this case, we're going to call that the posterior variance sigma n squared. And then if we read that off, we can then take the b part of this because we'll know the variance and we can just rearrange that to get what is mu. Or I should say in this case, we're going to be looking for mu n, the posterior b. Okay? So that's the strategy. And this is a general strategy whenever you're working with Gaussians, is if you can get this into this form, e to the sum quadratic, and then write with the ABC coefficients, then you can figure out what is the mean and the variance of that Gaussian from this general set of rules. Okay, so does everybody see kind of the general strategy? Any questions at this stage of the game? Okay. So again, just to kind of be really clear here, what are we starting with? We're starting with a likelihood. This is a constant. This is a random variable. We then give this a distribution, which is also a Gaussian. And now we've got two more constants that we have to sort of specify here. And then in the end, what we're going to show is that the whole thing as a posterior, by putting these two together, is also a Gaussian. And the whole trick is now, how do we determine what the mean variance of that new Gaussian is? And that's how we're going to use this continuous square trick. Okay. Right, so let's go ahead and do that. And basically, yeah, this is just a lot of executing algebra here. So it's just a little bit tedious, but not too bad. So, so if we write down the PDF for this posterior, the Gaussian, what we're going to show is a Gaussian, I should say, at the bottom. Again, this is proportional to the product of the likelihood times the prior, right? Now, if I wanted to say equals, I'd have it divided by p of x's by themselves. But that has no mu in it, right? So that's basically the normalizing constant of this posterior, and I can ignore that because the trick I'm going to use is ignoring the normalizing constant. It's basically showing us the quadratic and looking at the a and b coefficients and then ignore the normalizing constant because we are guaranteed it will work out just fine. Okay, so I'm going to stick to the proportional to argument. And this is also proportional to, because I'm going to leave off the normalizing constants for these two PDS, of course. Just writing down the Gaussian that we already know here. This is, again, a product of Gaussians, so I'm going to just bring the sum on the inside, the product on the inside becomes a sum, and I get that picture, right, for this likelihood, the product of the xi distributions. And then the p of mu is, again, proportional to, it has tau naught as its standard deviation, and now mu is the random variable, and mu naught is the mean squared. Okay? Just writing down the Gaussians there, right? And so, who can tell me, just to make sure everybody's awake, I'm not getting any questions recently, who can tell me what should be the next step? Yeah, louder.
The both with the sum.
Yeah, exactly. I'm going to combine these two, what's inside the exponent as a sum. Exactly. Yep. And so you can kind of see that we're going to get this quadratic in mu already, right? So yeah, so I'm going to bring the two exponents together. They become a sum on the inside. And notice I've got a sum of n terms here and another sum of one more term here, but all the terms are quadratic in mu. So this is just a mu squared type term here, and this is just a mu squared quadratic term here. And so I add all that up, and we're going to get a big quadratic in mu. And so now this is just an exercise in expanding this quadratic and writing it down in the ABC form of the standard form for the quadratic over there. Okay? So if we just expand out this sum and then add it to this, you'll see that what we get, making sure I don't mess it up, is the following. So do mu squared, the mu squared term here gets summed up n times, right? So I get n times the mu squared term in here. I then get 2xi times mu minus minus, so that gives me a plus. It cancels out the 2 over here, so I get 1 over sigma squared times, that gets summed up, so I get the sum of the xi's times mu. Okay? I'm going to ignore the thing that doesn't depend on mu now. We're going to throw that all into one big constant at the end. Then this guy over here, same kind of picture, just without the sums. I get a mu squared term, and I get a 2 times mu naught times mu. And now this has something that doesn't depend on mu, and this has something that doesn't depend on mu. I'm just going to call all of that C because I don't care about it. Okay? Because I really just need A and B to tell you what the variance and mean are. Okay, so the A term is this thing plus this thing, and the B term, so let's see, this is part of A, this is part of A, and then this plus this is my B term. Okay? So an A, notice, is just minus 1/2 times 1 over sigma squared. I should say now we're really solving for what we're calling sigma n squared. So let's just write it down in detail here. A is the sum minus n over sigma squared minus, 2 sigma squared, minus 1 over 2 tau naught squared. And so our posterior variance is just by rearranging that formula over there, it is, let's see, yeah, minus 2 over A, I think, right? Sigma squared, yeah. So minus 2 over A. And so I get 1 over that thing times 2, minus 2, and that is n over sigma squared plus 1 over tau naught squared. Okay, so that's my posterior variance for this Gaussian. And then now we have the variance. We can get the posterior mean by the B term, because the B term is just mu over sigma squared. And so the B term, if I add up pieces here, is 1 over sigma squared times the sum of the xi, which I'm going to write actually, just so I don't have to keep writing this sum, let's write this as n times the mean. So x bar means the mean of the beta, average of the x, which is just 1 over n times the sum, right? Right, and then this extra term 1 over tau naught squared times mu naught. Okay, so that's B. Now notice the mean is now going to be, if I again rearrange that formula, I've already got sigma n, and so now my posterior mean is B times my posterior variance. Again, just rearranging that formula. Okay? And so it's this thing, whoops. Yeah, this thing times this thing. So if I write that out, I get n times the mean divided by sigma squared plus prior mean mean naught divided by the prior variance. All of this thing divided by n over sigma squared plus 1 over tau I squared. Okay? Everybody happy with that somewhat painful algebra? It's really all just doing quadratic formula stuff, but it's somewhat tedious, I guess. But it's good to see it all the way through once for the simplest case because it does come up again and again. It's important to know this trick later. Or later in life, not just this semester. Okay, so any questions? I'm going to come back and we're going to talk about these two terms in just a minute, but any questions about that so far?
Where did that X bar come from?
The X bar is just, it's 1 over n times the sum of the xi's, and so I just replaced the sum of the xi's with n times x bar. So it's just, I just plugged in the mean just to simplify the notation. Yeah, and because it'll be a little bit better to understand this formula in terms of the mean data here. In just a second. Yeah. So any other questions? All right. Okay, so let's see. What exactly is going on here? So let me rewrite this equation upside down for, just take the inverse of 1 over sigma n squared. Then it looks like n over sigma squared plus 1 over tau naught squared. Right, I just take it 1 over that. Okay. Now, who knows in a Gaussian what a name for 1 over sigma squared? Somebody come across this before?
Inverse variance.
So inverse variance. I'm looking for precision. Yeah, exactly. So the precision. This is called the precision typically of a Gaussian. And as you can imagine, if sigma is let's see, if sigma is really large, then you get a small precision because it's not very precise. The Gaussian's kind of spread out. And if sigma is really small, then you get very high precision because the Gaussian's really tight, right? And so precision is the inverse of the variance, and it's kind of how we think of precision is your uncertainty in a value being precise means it's low variance, so it's inverse to variance, right? Okay, so what this tells us is that the precision is a little bit easier to think about than this formula for the variance. If I think that is the precision of the Gaussian, it's a little bit simpler to think about. What I get is that the posterior precision is just a simple sum of the precision of my likelihood, because as I take products of Gaussians together, I end up with, if you are familiar with Gaussians and standard error, you get sigma squared over n for the variance when you take the mean. So this is the precision of the mean statistic, the sample mean. So if I took this sample mean, if you remember from your statistics class, this is also Gaussian distributed. This guy here is Gaussian distributed with the same mean as the original likelihood and variance sigma squared over n. So the precision of the mean goes down at like a function of 1 over n as the n increases, right? And so the precision of my posterior is the precision of my sample mean plus the precision of my prior. Okay? So my prior had precision 1 over tau naught squared, right? And so what is this equation saying? It's saying that the precision of your posterior distribution, the uncertainty in your posterior of the mean of Gaussian is equal to it's two components. You have uncertainty that just comes from your standard statistics, which says that just the mean statistic has a certain uncertainty. So this is purely based on the data. The uncertainty in the mean from just your data is this uncertainty. But you have to add to it an additional uncertainty that comes from your prior. This is the uncertainty as to where the U parameter was to begin with before you saw the data. And this is the uncertainty that the data has associated to it. So you have to add those two together to get the uncertainty of the posterior. Okay, so that's how to interpret this equation here. Does that make sense? Any questions about that? Just interpreting that formula. Right. You can kind of just bring back to this equation we had for the beta distribution posterior. We also had kind of something that came from the prior and then something that came purely from the data. And so you see that this is, in general, this is the thing that happens with these conjugate distributions, is that the parameters look like, you can always see this is the contribution coming from the data, and this is the contribution coming from the prior. And so you should always kind of look for that pattern when you look at these conjugate priors and posteriors. Okay, so that is the how the precision, or I like to think it's the uncertainty in my mu parameter. It just adds up prior and likelihood to get the posterior. Okay, this formula is a little more complicated, but not completely intractable to get your brain around. If you think about this formula, what we're doing is we're taking we're looking for the mean of the posterior. We're taking, the mean of the data and combining it with the mean of the prior, but we're weighting this with the uncertainty or the precision of the data, and we're weighting this with the uncertainty or the precision of the prior. And so this is like a weighted sum and then divided by the sum of the weights. So it's just like a weighted average. So what you're doing for the posterior mean is a weighted average between, again, prior mean and data mean, and the weights on those, the weighted average here, the weights are just, again, the uncertainty or precision of those two prior and likelihood. Now notice, again, a general principle when dealing with Bayesian, or when you do Bayesian statistics well, a general principle is that as n increases, as your likelihood gets stronger and stronger, you observe more and more data, it washes away the prior. So the prior is completely inconsequential as n goes to infinity, right? If you have infinite data, then the prior is not going to change your result, basically, is the way to think this. No matter how strong, I mean, if obviously tau naught's got to be finite, no matter how strong that is, if n goes to infinity, this thing just goes to the likelihood model of the data, which is what we want it to do, because if you have infinite data, you don't really need a prior. Okay? In this simple case. Okay, so that's the way to think of those posterior parameters. We see that, yes, indeed, the normal distribution, likelihood, and prior are conjugate to each other, self-conjugate. You get, again, the posterior being a Gaussian, and the parameters of that posterior Gaussian are actually very easy to interpret in terms of the way they combine the prior information and the information you get from your data. And it's just basically averaging those pieces of information in both cases. Okay. Any further questions at this point? So just as a preview, in homework 1, you're going to do some actual data analysis, simple data analysis of just univariate data type things, but with not only this, but a few different options for priors on Gaussian. We'll get to some more things later this week and starting next week. And so this would be good to know how to do for the next homework. You'll get some hands-on experience with it with real data. Okay, I think that's everything I was going to say about the Gaussian. Right. Okay. Yep, that's all for Gaussian. Okay. Right, as I was saying, these conjugate priors that these two examples, and really almost all the examples of conjugate priors that come up in practice come from distributions that are well-known, well-studied, and they all fall into this category of distributions of family called exponential family. Okay, and that's what we're going to talk about next. And so a somewhat general framework for all of this is called an exponential family. Of probability distributions. And what this means is if your random variable x has a density, or this could be again discrete or continuous. So this works in actually both of these cases. We're going to see that the Bernoulli and the normal distribution are both in this family. If your data x depends on some parameter theta, and now theta could be a little bit wishy-washy. Theta could be just a single number, like we have here. Theta is a single number here, and then like mu is a single number here. But it could also be a vector of a number. So it could be like a mu and a sigma squared, so a two-variable thing, or it could be a mean vector and a covariance matrix in the multivariate Gaussian case. So this is, and likewise, x could be a vector value random variable, or it could just be a univariate random variable. We're just going to kind of stick to univariate things for the most part right now, but this extends to multivariate. Okay, so if your distribution, or PDF I should say, is in the following format: some function h of the x, vector value, times exponential of some function eta of your parameter theta times t of x, where again t is just some function of the x minus a, which again is just some function of theta. Okay? So if you can take your PDF or PMF and rearrange it so that it looks like that equation, where h, eta, t, a can be kind of whatever you want, then your random variable x is in an exponential family. Okay? And that's basically the definition. Okay. Now, why is this particular format of equation of interest? I'll actually rewrite this. Again, notice this a of theta doesn't depend on x, so it's really like the normalized constant, right? So if I just define g of theta to be, let's see, exponent of a of theta, then this is equivalent to h of x divided by g of theta times this thing. Okay, so the real part inside the exponent is really just eta of theta times t of x. And if you have, by the way, vector value things, this could be a vector dot product with t of x. That's the vector version of this. So you can write this in terms of multivariate things if this dot is not multiplication, but actual dot product between two vectors. So that's how you get to exponential family for multivariate things, just as a side note there. Okay? So notice that the first thing to notice about this is that x and theta don't intermingle with each other outside the exponent. They only interact with each other inside the exponent, and they only interact linearly with respect to each other. So they're only multiplied by each other. They're not like square or square root or anything like that. Once you get it in terms of eta and this t, which we're going to build into a little bit in a minute here. Okay? And so the exponential family basically says you can put your parameter into some form through a change of variables, this eta change of variables, and x through a change of variables, this t change of variables, if you will, such that they only interact with each other multiplicatively inside an exponent, and that's it. Okay? Other than that, the rest of it is, they would be independent if it weren't for this interaction. They would just completely factor apart from each other, but they have just this particular type of interaction. And we'll see that's actually really critical to get these conjugate priors here. Okay? The next thing that's important about this exponential family is that this particular thing, t of x, is called a sufficient statistic. And really, I should probably write this. If I have x1 through xn here, notice this just becomes the sum of the t of xi's inside here. So your sufficient statistic for a sample of x1 through xn is really just a linear combination of things for a single number here. The important property of this sufficient statistic is that the word sufficient statistic means the following. It means that if I know t of x, okay, where t, I really should say t of x1 out to xn. So this sufficient statistic is just, it combines all my data x1 through xn. If I know that sufficient statistic, then I can throw away the data. And everything I could infer about the parameter theta is contained in that sufficient statistic. That's the definition of the phrase sufficient statistic, is that you don't need the data if you know the sufficient statistic. If all you care about is theta, I should say. If you want other information, obviously, don't throw away your data. But if all you care about is theta, then you don't need anything other than the sufficient statistic. And saying that in terms of probabilities, the sufficient statistic property means the following, that anything about the probabilities given the sufficient statistic and the data is basically, there's this kind of conditional independence that this is equivalent to the density given just t of x. I can throw away the x. And again, I can write out the xi's there if you want to write it out. In longer form, really more interesting is I have a whole set of n data points, and I have all these n things I can throw all those x's away. And this posterior probability of theta is really independent of the x's given the sufficient statistic. Okay, so that's the first important property. And I think the fact that this is true is hopefully clear from this exponential family definition, right? So if I know t of x, then the probability of theta, the h of x is actually not important because it's really just a normalizing constant in this whole, when I flip the conditional there. Okay, so I can basically tell you anything you want to know about theta if I know t of x, even if I don't know x anymore. Okay, so that's the first key property of the exponential family. Let's see. Right, the next, well, yeah, before I get to the real link we want is with conjugate. Why is this conjugate priors involved here? But before I do that, let's actually see that the Gaussian and the Bernoulli, like I said, is in this this type of form. Okay, so looking at, again, this is the key part here, trying to see that we get this. It's maybe a little more obvious looking at the Gaussian PDF because there's an exponent there, e to something. The beta Bernoulli thing, it's a little less obvious that we get something in this form, maybe, but we'll see that we do. So let's take a look at the Bernoulli. And so that would be, that's why I left it up here. This is, again, a likelihood we want to see that that is in this form, so it's an exponential family. So let me come over here, I guess. So that likelihood function can be rewritten if I think of this product by I think taking logs so that I get this thing to look like an e to the something. Then right, yeah. And what I get is e to the log of that. Actually, let me write it out. Not the final answer. Let's write it out kind of step by step. So e to the log, of course, is just the identity. So I can just put this inside there. Like so, right? Everybody, that was that first step. And this, again, I'm going to keep the exponent because I want it to look like that over there. But now I'm going to bring the log inside here, and I get a sum of x y's times log theta plus this sum of 1 minus x y's times log 1 minus theta, and okay, really happy with that. So I just brought the log inside the product, just turned it into sums, and brought the exponents down. And then with with a little bit of now, so I'm still not, notice I've got thetas over here, thetas over here. I need to kind of collect all the thetas into one term time some big term in x's, right? That's kind of my goal. Okay. So yeah, so notice this sum of the 1 n times is going to give me just the number n minus the sum of the xi's. So, and if I collect, I feel like I'm making the sign. Okay, so then if I collect the sum of the xi's and the minus sum of xi's, I can make that, the log is like a log minus a log, so I get a 1 over, or a theta over 1 minus theta inside the log. So I get the sum of the xi's times a log theta divided by 1 minus theta, and then this n times log 1 minus theta. Okay? And so this sum is t of x. This log theta over 1 minus theta is my eta of theta. And this n log 1 minus theta is my, you have a minus sign, yeah, this is my, I guess, minus a of theta, which is just your normalizing constant in terms of the x's here. Okay? So we can see that there's a little bit of mathematical tricks. We can squeeze the Bernoulli distribution into this format of exponential family. Okay, so question, yeah?
So that means we can convert any distribution into exponential or the...
No, not any distribution. Yeah, not any distribution can do this. So yes, that's a good question. Like, why can't I just do this for any distribution? It's a good question. It's hard to prove a negative, but you can't do it. So this x log trick, you might imagine, why can't I just do that for every distribution? You can't do this for every distribution. And rearrange it in a way that you can separate the only time the x's interact with the thetas is through a completely separate, I'm pulling them apart. So for this thing times this, some term in x's times some terms in theta.
So is there any list of distributions which can be converted, which cannot be?
Yeah, so the entire list of all things that are exponential family are on the Wikipedia page, I believe. I believe they have it. Or I'm thinking of the conjugate. There's a giant table of conjugate distributions, but I think maybe they don't talk about everything that can be exponential. But they have extensive names of things that can be. But I can give you a few that are not. So a t distribution, so students' t distribution is not an exponential family. The Cauchy distribution is not in the exponential family. So if you look up these distributions, look at their form, you might try to convince yourself that, oh yeah, if I do this x log trick, or actually, some of them already, Cauchy already has this x thing in it, but anyway, if you look at the form, you can convince yourself that when you do this, they don't, the parameter and the x's don't really separate, is kind of what you'll see. Yeah. I'm trying to think of another, I can't think of any others off the top of my head that have names to them. But yeah, those are two examples that come to mind. Okay, so yeah, so Bernoulli does work out this way. Now notice, one thing I want to say about the eta of theta. The eta of theta is often called the natural parameter for the distribution. And you could then do a change of variables so that this term is in terms of, so I could call this thing eta, so I could just call this equal to, p to the sum of my x's times eta. And then rewrite this so that my a is just rewritten in terms of eta also. So this would be an alternative form of your exponential family where now you've just done a change of variables to not be concerned about the parameter theta, but in this case be concerned instead with the parameter log theta over 1 minus theta. This, by the way, is, anybody know the name of this function, log theta for 1 minus theta, when theta is between 0 and 1? I've seen this before.
Log ratio.
Yeah, it's called the
Additive log.
yeah, well, the logit or logit, depending
Log
on
ratio, I think.
log what?
Okay.
You might be right. I'm not sure what
It's a log ratio function as well. We use
Say again, log what?
log ratio.
Log issue?
Log ratio.
Oh, ratio. Oh, yeah. Like a log odds. Yeah, right,
Yes.
exactly. Yeah, like a log ratio or log odds. Yeah, that, you're right. It comes up in that type of case, and in general, logit or logit. I'm not sure how people pronounce this. I think it depends on who you are. Is another name. Yeah, log ratio. Yeah, you're right. That's another name for it. Yep. So yeah, so this is so it's actually the log odds of a 1 versus a 0, right? This is the probability of a 1 versus probability of 0, the odds of a 1 versus the odds of a 0, and you've got the log ratio, log odds of 1 versus 0. That is the so-called natural parameter of a Bernoulli distribution, meaning that it's just if you get a sufficient statistic, and notice the sufficient statistic is what we use typically where you sum up the x's, we call that k, where it's just the number of ones that you observe in your sequence of n x's, right? So you take the number of ones you observe is your sufficient statistic. If I tell you how many ones I observed, and it seems pretty obvious, but if I tell you the number of ones I observe, I can throw away the exact sequence of zeros and ones. There's nothing you need to know to understand theta other than the number of ones that you observe in a sequence of n. I don't need to tell you the exact order of the sequence, right? So that's why this is a sufficient statistic. You just need that single number. And then this says that the logit is, the log ratio of theta is the natural parameter, so it just looks like compute your sufficient statistic and multiply it by that natural parameter. And you can do your inference directly on the log ratio here. You could actually look at the posterior distribution of eta instead of the posterior distribution of theta, if you were so inclined. So anyway, that's just terminology, the natural parameter. Oh yeah, now the final piece, before I run out of time, I want to get to the whole punchline, which is that these exponential families give you conjugate distributions. So let's see that. Maybe as a exercise for your own, like outside of class for fun, since this is lots of fun, you can convince yourself that the Gaussian distribution is an exponential family, and figure out what is the sufficient statistic for the mean. Just the mean, again, keep the variance constant and just look at the mean and figure out what's the sufficient statistic for the mean and what's the natural parameter for the mean. And you'll see it's a little bit funky. It's not exactly, but it does make sense. And if you're lazy and don't want to do it on paper, just look at the Wikipedia page. But you can see that you get the same exponential family form. Okay, so last point I want to make, and it is just a quick 5 minutes, hopefully to cover this last point, is anytime I have a likelihood in the form of an exponential family, it has a conjugate prior. That's the last point I want to make. That's the last property of exponential families that's critical for our discussion. So if I'm going to if I've got that p of x given theta, then I can always define p of theta, my prior distribution for my parameter theta, to be proportional to something of the following form, which is x, again, eta of theta times some parameter, I'm going to call it nu, Greek letter nu, minus, and that's just, if you're univariate, that's just a scalar, or it can be a vector if this is a dot product, minus, again, some scale factor alpha, just some constant alpha, times the same function a of theta that I have up there. Okay? And if I find the prior in this form, which is not exponential family necessarily, because there's no x and theta here, it's just a theta. So it's just a PDF of theta with hyperparameters nu and alpha. Now I put together the posterior, and it's pretty easy to see that the posterior will be of this form also, right? So this guy is proportional to the product of this thing times that thing. So just writing it out, I'm going to take that thing first, so I get h of x times x sufficient statistic times eta of theta minus this a of theta, and then times this prior I've defined, which is x eta of theta times nu minus alpha a of theta, so I bring that through. Okay, and again, same trick, I'm going to add the pieces inside the exponent, and this whole thing is proportional to, again, this h of x is a normalizing constant, so I don't care. Frankly, actually, I'm kind of, this really should be a product of all the h's, and this t should be the sum of all the t's. I'm kind of leaving out because I forgot I'm doing x1 through xn here. Anyway, then I multiply these together, or add up the exponents, I should say, and of course I get eta of theta times the t of xi, sufficient statistic plus eta, or nu, and then minus 1 plus alpha a of theta. Okay? And so it's in the same form as this, just replacing nu with the sufficient statistic plus nu, but still that's some value, and then alpha with 1 plus alpha, and it's in the same form. Okay? So you get this conjugate prior, or this prior is always conjugate to the exponential family. If you find the eta, what is the natural parameter, and you find this a of theta, that puts you in some class of exponential family, and it always has a conjugate prior. Okay. The last point I'll make just briefly is that notice that this is very much like when we saw in the Bernoulli case that putting in a prior is like putting in pseudo observations. It's like putting in pseudo observations of the number of ones and zeros I might have seen in a prior data set. This is very similar. This nu parameter in your prior is basically a pseudo sufficient statistic, pseudo observation in the form of a sufficient statistic. And this alpha, well, that's a little bit harder to think about what the alpha does, but that depends on what the a of theta is. But the nu can very often be thought of as like a pseudo observation. So these conjugate priors almost always can be interpreted. In fact, the normal distribution that we went over also can be interpreted as pseudo observations, and you're going to have in the homework exercise how to interpret that way and to use the analyzed data. Okay, that's the last point I want to make. Any other final questions? All right, great.